All right, let's work out the assignment questions. Now, first question says explain what is meant by the term electric field strength. Um, Whenever we're talking about electric field strength, all we're really talking about is the force experienced, right, at some point per unit charge, right? So you could say that electric field strength is the force experienced at some point per unit charge. And we know that every charged object will have some type of electric field. We know that the positive has its electric field being radiated outwards, stuff like that. And then we know that the negative charge has its electric field being radiated inwards. So yeah, so that's what electric field strength is. Now we have a particular question here that tells us or asks us to, based on this question, it is linked to Millikan's oil dropping experiment. And remember when we talked about Millikan was the one who pretty much found out what the charge of an electron really is. And what he did was to just use some type of oil dropping kind of an experiment, allow the oil to levitate itself in between a potential difference, right? Now, during that experiment, he had to obviously find a way to balance the system. Follow me? Now, based on this, we have two parallel plates sitting right here in front of us. Now, one plate is positively charged. If this plate is positively charged, we know that any charged object that is positive, the electric field will be moving from positive outwards. So we expect that we'll have some uniform lines. Forgive me if my lines are not straight, but yours should be straight. They should be uniform, coming from the top plate to the negative, right, or to the zero plate, I should say. Because this doesn't necessarily tell us if it's zero. It just tells us that it's zero potential. All right. So having said this, now the question asks us to state whether the charge on the oil drop is positive or negative. Now, the question told us that the oil drop was stationary, right? Which means that the upward forces, right, must be equal to the downward force. The only way this charge will be able to be stationary inside of this electric field is if the charge, overall charge on the oil droplet, or the oil droplet rather, is negatively charged, and I'll explain to you. Now, based on the plate, the top plate is positively charged, right? That positively charged plate is going to give off a positive force that is directing downwards. Follow me? Now, if this charge was positive, I should say, if this oil droplet was negative, right? I said the wrong thing again. If this oil droplet was positive, then we can expect that there will be a force of repulsion. Good? So it means that the oil droplet would have been pushed away, and that's not what you actually want, right? You actually want it to be balanced. So the best way for it to be balanced is if you have a force of attraction. So the negative and the positive will attract, right? And yes, they attract, but it will not move because of the fact that you allow the upward force to be balanced with the downward force. So we can agree that it's going to be negative because that negative charge will tend to attract itself. So if it's attracting itself, then it is going upwards. You follow me? And if it's going upwards, then this now can basically tell me that that is the situation that would allow, this charge to become balanced at some point. If it was positive, it would have been going down, right? And you don't want it to go down, because if it goes down, then it's not going to be able to balance, because you will have two forces going down. You'll have the force of the plate acting down on it, and then you will have the weight acting down, and you don't want that. So to get it negative, the negative and the positive will attract. All right, so it says to us that complete the free body diagram to show the force acting on the oil drop. I should ignore the fact that upthrust, we should ignore the upthrust force. So let's imagine that this is our oil droplet. Based on the fact that our oil droplet is negatively charged, right? The negative and the positive plate is going to attract. So there's going to be a force acting upwards. That force is going to equal to the electric field times Q, because we know that E is equal to F divided by Q. So if we transpose, we know that that is equal to that. The other force that is acting on the system is going to be the weight force, right? And we know weight is equal to mg. The question gave us what m is, right? Now, if the question goes to us and tells us that we should find the magnitude of the charge on the oil drop, right? All it wants us, because at the point when the system is balanced, there is no acceleration. So we can say that the net force is equal to 0. What are the forces? The forces that are acting is the upward force and the downward force. So well, let's call it EQ is the upward force. That's going to be positive. The force acting down is going to be negative, so it's going to be mg is equal to 0. Now, by way of just transposing, we get EQ is equal to mg. We want Q to be the subject. So if Q becomes the subject, then we have mg divided by E. And if we were supposed to go ahead and put in those values, so the mass was given to us. The mass was 1.2 times 10 to the minus 14, right? And we know that gravity constant is 9.8. Divide this now by the electric field. We could have found the electric field via this equation to say that E, because we're dealing with parallel plates, V divided by D, right, could tell us what the electric field is. We know that the volt is 5,100. Divide that by the distance, 2 times 10 to the minus 2. So when you do all of this, we're supposed to get a value of 2.55 times 10 to the 5th power volt per meter. So that's our electric field strength. So we're dividing that number here. By way of dividing this and everything, we get that the Q is equal to 4.61 times 10 to the minus 19 coulombs. So that is the overall charge on the oil drop. Now it says calculate the number of electrons that would have to be removed or added to a neutral oil drop for it to acquire discharge. Now, in order for us to know that, we have to find out how much charge is really on the thing. And in order for us to do that, we know that Q, right, can be expressed qualitatively as N times E, right? We know that the charge here is going to be negative because we said it previously that it has to be a negative charge for this thing to actually work, right? So providing that this is a negative, then the overall charge is negative 4.1 times 10 to the minus 19. We're trying to make n become the subject here to find out the number of electrons that is really on this particular oil drop. So we'll divide this by the charge of an electron, which is negative 1.6 times 10 to the minus 19. So by way of doing this, we should get a value of 2.88. And this, because we know that you can have 2.88 electrons, right? We just simply say it's going to be 3n. So either we're going to have 3 electrons being removed, right? Or 3 electrons added to to a neutral uh, oil drop for it to acquire this charge. So in this case, we would add 3 electrons, right? So that's essentially what you were supposed to do there. As regards to this question, this is just an electric field type of question where it wanted to prove something, right? They said, let me see what the question here is saying. So they're saying that at point P, right, its electric field strength is approximately 0. Now at point P, right, it is in between 2 charges. Both charges are positively charged. What we can essentially do is find out the net electric field that is going to act on that point and see if it actually makes sense. So we could essentially go ahead and do this. We could go ahead and try to find the electric field. So the first thing we'll do, we know that E is equal to K times Q divided by R squared, right? So if we want to find the electric field from Q1 to Q2, then not Q1, but from Q1 to point P, they would have to use this formula. So we're trying to find E that is due to Q1. So K is equal to 9 times 10 to the 9 times Q1. Q1 in this case is 3 times 10 to the minus 6. Divide this by R squared. R in this case is that distance of separation. 8.1 times 10 to the minus 2. All of this is being squared. When you work out this, you should get that E1 is equal to 4.12 times 10 to the 6 newtons per coulomb. Now as regards to this Q1, because Q1 is positively charged, then we expect that the direction of the electric field will essentially be going downwards, right? So we can put a negative sign in front because it just shows the direction for this key, for this event. Now we want to also find what is the electric field Q2 is going to have on point P. So we would go ahead and work that out to say E2, right, is equal to KQ2 upon R squared. R in this case, because the entire distance is 20, right, between both charges, and we know the small piece, we can then subtract 20 minus 8.1 centimeters to then find out what is the overall distance between the point P and point and Q2. So in that event, that value is going to be 11.9, right? So that will be the distance. So we can put in that value. So 9 times 10 to the 9 times 6.5 times 10 to the minus 6, good, coulombs. Divide this now by 11.9 times 10 to the minus 2, all of this squared. We should get that E is equal to you would get that E is basically equal to 4.13 times 10 to the minus 6, positive 6 rather, positive 6 newtons per coulombs. So if you look at E2 is positive. So the force that you experience is going to go up, right? And of course, then the electric field will go up in the air like this. So it means that this is going to be actually a positive electric field because it's pointing upwards, right? So if we're trying to find the overall net force that is acting on point P, so not net force, but net electric field, I should say. Net electric field at point P, that is then equal to E1 plus E2. But we know that E1 is negative 4.12 times 10 to the positive 6, right? Plus E2, which is positive 4.3 times 10 to the positive 6 newtons per coulombs. By way of just subtracting this, you realize that it's approximately equal to 0, right? So this is how you would go ahead to prove this, right? To say that the net electric field at point P is actually equal or approximately equal to 0 newtons per coulombs. So that covers that question. Then the question go to us and say to us now that if a charge of positive 4.5 microcoulombs is placed at point P, it says state the magnitude of the force acting on this charge. The question is a 1 mark question, so it means to say then it's not supposed to require so much working out, or actually it's not really supposed to require no working out. Hear me out now, guys. If at point P there is no electric field being experienced by both of the charges here, then it tells us that if you put a charge there now, it still wouldn't experience an electric field. You understand? Or it wouldn't experience any type of force at that very point. Let's see. Right? So it says state the magnitude of the force acting on this charge. So just remember, because it's at point P, right? And point P, there's no electric field that is experienced by Q1 or Q2. Then if you put a charge there, then there won't be a force that will be experienced, right? So in this event, we can say that it is equal to 0 newtons. Now it says now the positive 4.5 microcoulombs charge is moved from point P to a point halfway between Q1 and Q2. It says explain qualitatively why energy would be needed for this to happen. So remember now, that Q1 is positively charged. Q2 is also positively charged. And then now you take a next charge and I put it. This is an next positive charge that you're putting in between two positive charge. Obviously, if you have to go put if you're putting that charge somewhere in between two positives, then you would obviously need to do some amount of work to move that electron halfway in between there, right? Because you would obviously be experiencing some type of force of repulsion. So the positive 4.5 microcoulombs is a positive charge. So if you're bringing that positive charge towards the Q2, both forces are repelling against each other. So you'd expect that you need energy for that to happen, for you to move that. Now, what if it was a negative charge? Then you would expect that you wouldn't need that external energy because there would be a natural force of attraction between the positive and the negatives. All right. Here we have a capacitor question. It says now the capacitor is charged to a potential difference of 100 volts from an electronic charging unit in the camera as shown in the diagram. It says calculate the energy stored in the capacitor. Now there are several equations that we can use. So U is what we generally use as a symbol to talk about the energy that is stored. And if you can remember, this is equal to a half Q times V. If you remember that graph that we had looked at the time, where we had Q over here, so, and then we had V, and we said that in order to find the energy stored, you would find the area underneath the graph. And based on this type of graph, it's a triangle, so you know it's half base times height. So that's how you can remember one of the equation. Now, we don't know the charge that the capacitor has, but if we know that C is equal to, well, if we know Q is equal to C times V, right, then we can make a substitution in this equation that says if we substitute Q, we get a half times C times V squared, and this is equal to U. So essentially this is the equation that you would use, and we can then put in the values, right? So if we go ahead and put in the values now, we have a half, so U is equal to a half times the capacitance, which is 180 times 10 to the minus 6 times V squared, so V is 100. So we can work this out. So 0.5 times 180 e to the minus 6 times 100 squared. That actually gives us, and you can check, that U is equal to 0.9. Well, this is energy, so it's joules, right? 0.9 joules. Yeah. Yes, so that is the energy that is stored. The question asks us now, what is the work, or calculate the work that is done by the battery. If you can recall, whatsoever potential energy, whatsoever energy that the battery is storing, that's the same amount of work that was required for it to store that charge. So therefore, the work done by the battery is actually equal to Q, is actually equal to U, I should say. So that's going to be 0.9 joules. Question goes on to say now that when a photograph is taken, right, switch S in the diagram, above, well, on the next page, is automatically moved from point A to point B, and the capacitor is discharged through, well, this discharge across the flash tube. The discharging circuit has a resistance of 1.5 ohms. Emission of light from the flash ceases when the potential difference falls below 30 volts. It says calculate the duration of the flash. For us to answer this question, we have to take into account the equation that links whenever we have a discharging capacitor. So we know whenever a discharging capacitor, you have a curve looking like this, and there's a particular equation that we can use to characterize this kind of graph, and that equation is V is equal to V naught, right, times E raised to negative T RC. Good. So having this equation, we can find the time constant. So remember, time constant is your RC value, right? Time constant. We know the capacitance of the capacitor, that is 180 times 10 to the minus 6 farads, right? And the resistance is 1.5. So if we go ahead and multiply that, we essentially should get that RC, or we can call it time constant, is equal to 2.7 times 10 to the minus 4. And the units is, you can put it in, I don't think we should put it in seconds, but let's just put it in ohm farad, because we're times in ohms and farad. So we can leave that as that for now. So once you know that value, and you know the initial amount of charge that, or not charge, but voltage that you started out with, so V naught is going to be 100. Good. And then we know the final amount that is left, right, when the flash ceases. So the flash ceases when it is when it falls below 30 volts, right? So basically at 30 volts you can say that the flash ceases. Good. So that's our final charge, well, not charge, final voltage that would be left in a sense in the capacitor. Now we want to know the time when it reaches at that very point. Good. So we're left with our equation to say that e to the negative t, divide that now by the 2.5 times 10 to the minus 4. We can bring certain things across the equation. So we could say 30 divided by 100 is equal to e to the negative t divided by 2.7 times 10 to the minus 4. When we divide up this on the other side, we get 0.3. All that is equal to e to the minus t upon 2.7 times 10 to the minus 4. Now, because we want t, the e is blocking us from finding t. In order for us to get e, to get t, we have to ln both sides. So we're lning or find the natural log of 0.3. Whatsoever you do on that side, you do it on the other side, because we know ln and e cancels out. So when it cancels out, we will be basically be left with this thing. But before we do that, let me just point out something. So whenever you have the natural log, whenever you have ln e tells us that this thing in the power comes down in front. So we will therefore have negative t divided by 2.7 times 10 to the minus 4, right, multiplied by ln e. Good. And all of this is equal to ln 0.3. So we know ln and e cancels out, so we're left with this type of fraction. We can then, go in our calculators and put in ln 0.3. When you put ln 0.3, you get negative 1.203 something. And then because you want t, we're going to just take the denominator and multiply it by the negative 1.3. So let's put it somewhere up here. So we have negative 1.2 being multiplied by 2.7 times 10 to the minus 4, right? And all of this is equal to negative t. So let's see what we have now. So 1.2 times 2.7 raised to the minus 4 supposed to give us a time of 3.24 times 10 to the minus 3 seconds. Follow me? This is still minus. I know it's equal to minus t. The minus can cancel out. You can just divide through by minus, and then you would realize that the time at which the capacitor will reach to a value of 30 volts when the flash ceases, the time is going to be 3.24 0.24 times 10 to the minus 3 seconds. So that's really fast. So the capacitor really discharged a whole lot at that very point. Alright, I believe that answers all of these questions. So that's about it. If you have any questions, you can always reach out to me.